go ahead and read through this one, and then we'll discuss. Okay, so this one fits on this page, so we'll just talk about all of it here. Some interesting things happening. We've talked a little bit about this reaction and esterification, trans-esterification. So some potential questions, right? What are defining characteristics of a carboxylate salt? The differences in saponification of sodium or potassium hydroxide are used, right? How would this saponification number change? What changes in the size of the triglyceride? Okay, a number of interesting questions coming off of here. Let's try question 1. All right. So which of the following equations represents the products of the chemical reaction of saponification occurring in the third tank? So I'm going to go back to the experiment. What's happening in the third tank should have the reacted product of the CH3 COO C2H5. That is the ester, and the NaOH. So it should have the product of those two. Basically, the saponification of an ester is going to give us a carboxylate salt and an alcohol. Right? So saponification is occurring in the third tank. So relevant concepts here. An ester is going to break apart when it's saponified into the carboxylate salt and the ROH, the alcohol. So with the reactants that I have, that is ethyl acetate, I should get the carboxylate salt and the alcohol. So that corresponds to B. All right. Quick way to check this to make sure that I've got a correct answer is to just do a stoichiometric count, right? Make sure to count that the reactants and all of the atoms, how many carbon atoms, how many hydrogen atoms, how many oxygen atoms, sodium as well, are equal on the left-hand side and on the right-hand side. If they're not equal, then the answer must be incorrect, okay? Or I must have done something incorrectly. All right, let's try number 2. All right, so for the saponification reaction to run to completion, which of the following conditions must be true? Okay, so completion means everything reacts and reaction finishes. So which of the following must be true? We'll basically have to do process of elimination here, whether moles of ethyl acetate equals moles of ethanol. Right? The information in the passage is ethanol is a product of the ethyl acetate saponification in a 1-to-1 ratio based on the stoichiometry, okay, 1-to-1 molar ratio. So looking at a bunch of these, if it has to be in a 1-to-1 molar ratio, that makes A look like a very good answer. Right? Moles of ethyl acetate equals moles of ethanol. As long as those two are equal, I know that the reaction has run to completion. Now, what about B, C, and D? So the concentration of ethyl acetate and the concentration of ethanol. The problem with those two answer options is it only works if the volumes are the same, right? Because if the volumes are the same and the concentrations are equal, then it means that the number of moles is the same. But I don't know that that's been held constant, so I don't know that this would be true. Okay, for C, the volume of ethyl acetate and the volume of soap, this has basically the exact same problem as B. The volumes alone don't tell me anything unless I also know the concentrations, and I don't know what's happened to that here. And for D, the weight of ethyl acetate and the weight of the soap plus ethanol, again, we are looking at this from a perspective of the moles, and so the weights don't really tell us much. Okay, because we need to convert the weights into moles. In fact, if the weights were the same, we would basically know, functionally guaranteed, that the moles are not the same because they don't have the same molar masses. All right, let's try number 3. Okay, so saponification number was a new concept that we've seen before, right? We've never talked about this before, not a big deal. The passage tells us how to calculate this, right? It tells us what the saponification number is. So the saponification number is the number of milligrams of base that has to be added in order to saponify 1 gram of the reactant. Okay, that is either the fat or the oil. Okay, we know what the ethyl acetate's molecular formula is. We can calculate its molecular weight, 88 grams per mole. So again, the question is the number of milligrams of base to get rid of 1 gram of the reactant. Okay, so 1 mole of the ethyl acetate should react with 1 mole of the potassium hydroxide, which has a molecular weight of 56 grams per mole. So basically it's just a ratio of the two. 56 over 88 is roughly 60 over 90, roughly 0.65. Okay, transforming that into milligrams, we get 650 milligrams. Okay, 0.65 grams is 650 milligrams. So that's my saponification number. Okay, now very quickly, why is it okay for me to simply say the number of milligrams of base that has to be added is equal to the molar masses divided by one another? Okay, because it's grams per mole divided by grams per mole. How did I get units of grams from that? Okay, if I were to because these are both in the same units, if I were to convert these into number of moles per gram, I would still be comparing the exact same units. So if we think about it as, let's assume that they have the exact same molecular weight, that they're both 56 grams per mole. Then it means that I just need, in a weight ratio, 1 to 1, right? So it would be 56 over 56 equals 1. The answer would be 1,000, okay? 1,000 milligrams, 1 over 1. In this case, I actually need less potassium hydroxide to get rid of, or to react 1 mole of ethyl acetate, and the amount less is given by this ratio of the molecular weights. Okay? So divide the two, I get 0.65. That's how much less, or that's the actual amount of the potassium hydroxide that I need. Right? So that's question number 3. Let's try question number 4. All right. So graph-related question. Right, and this is a pretty tricky question. So again, let me just fix this up so that it actually matches what you see on your slides, so that we're talking about the same thing. There we go. All right, so the question here is about the relationship between the molecular mass of the fat or oil and saponification number. So again, very important, look at the axes. Saponification number is on the y-axis, not on the x-axis here. And the molecular mass, presumably of the fat or oil, is on the x-axis. So what happens to the saponification number as you increase the molecular mass of the oil? Okay, again, saponification number is the measure of the amount of KOH in milligrams that has to be added to completely saponify a fat or oil. Okay? So, concepts here. Saponification number, we can basically write that out in an equation as S, saponification number, equals the base over the fat, or the oil. So the molar ratio that's required remains unchanged, right? It's whatever, 3 to 1, 1 to 1, whatever the case may be. That ratio remains unchanged. As the molecular mass increases, right, then the amount of base remains the same because it still just needs to be done in a molar ratio. So as this denominator increases, then that is this denominator here, as this mass increases, the value of this expression, base over fat, decreases, so the saponification number decreases. This is an inverse relationship. Okay, so it should have this curve. It's not going to be linear because this inverse relationships are not linear decreases. Okay, now if that kind of threw you for a loop, let's just sort of think about this broadly and more conceptually. So if I have a fat with a very low molecular weight, it's going to have more moles per gram, and therefore it's going to require more base, right? My saponification number for a very low molecular weight fat is very big because it has a lot more moles per unit gram, right? So my saponification number should start very high. And then as the molecular weight increases, let's say it becomes a very, very big molecule, that means that per gram, I actually have a very small number of moles because each molecule is very, very big. And so my saponification number goes down. So I definitely know my answer is going to be C or D here. The question is just the shape, and that's given to me in this graph. It's an inverse relationship, so it has to follow this shape. All right? Try question number 5. All right, so we're being asked about the electrical conductivity of the third tank, starting with those 2 supply pipes when they're opened, and then when the reaction is complete. So what should we see? Well, if we think about what's happening in the third tank, so the third tank starts with an electrically neutral solution, that's what we're told. And the basically the electrolyte concentrations increase the electrical conductivity. We are adding electrolytes to this, right? NaOH, and we add the carboxylate salts. Both of these are electrolytes. So the electrical conductivity should actually increase over time because the amount of electrolyte is increasing over time. Once the reaction is complete, the concentration of the electrolytes remains unchanged, and so the conductivity doesn't increase beyond that. So what I see is electrical conductivity increases over time, then becomes constant. That's consistent with how the experiment is run. All right, last question. Okay, so the source of NaOH used for the reaction was mislabeled and was actually KOH. This is a classic kind of question where they really ask you to think critically about the experimental design and the assumptions that we make behind certain calculations. So what happens if you assume something is greater, but it's actually smaller, or vice versa? Okay, so it was actually KOH instead of NaOH, and consequently, the reaction was found to be 30% less efficient, producing less product overall than when NaOH was used, right? Because KOH has a higher mass. So what explains the discrepancy in the product quantity, right? Well, we just kind of already talked about that. Relevant concepts here can sort of do a process of elimination. For A, KOH is a weaker base and doesn't ionize as well, meaning it produces less product. KOH is actually a stronger base than NaOH. And both bases are very, very strong. They're both going to dissociate almost entirely. So that answer is not very good. Let's look at C. The smaller size of sodium ions better stabilize the transition state of the reaction mechanism. Really, there's no clear correlation between the size of the ion and the stabilization. It's beyond the scope of the passage, and it's not really clear that any transition state needs stabilization by a positively charged ion. That's not part of this reaction as far as we're concerned. For D, the reaction was simply not run long enough. KOH is a slower reagent and needed to be given more time to reach completion. Okay? The thing is, the question already states that the reaction is less efficient, right? So given the substantial similarity, given that these are very similar bases, it's not clear why one would take much longer than the other. So again, it's beyond the scope of the passage of the question. Okay, our answer here is B. KOH has a higher molar mass. So when we assume we've added a certain amount, so we've weighed it out, we thought it was one of them. We thought its molecular mass was a particular number. Its actual molecular mass was something else. So we weighed it out, and the number of moles was actually different from what we anticipated, because its molecular weight was different from what we anticipated. And so therefore, we're not going to get as much reaction. Okay? So, takeaways from here. The scenario analysis, like in question 6 that we just did, is a pretty tricky place to score points, right? These questions are going to take some time to think through. So if you come across a question like this and you're not sort of intuitively drawn to any particular answer up front, skip it and come back to it. These generally are big time sucks because you have to think very often from a couple different angles to try to wrap your head around why the relationship is the way that it is. So don't get thrown off by these questions. They are intended to be difficult. They are challenging. If you don't have a problem with them, great. But if you do, don't linger on these. It's not really worth your time to try to score this 1 point if you lose time to score other easier points.
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you've found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than Exam Crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, we offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.